now going to be moving on to the next part of our demo, section 5.5, floor planning. We're now ready to start the floor plan stage of our design, and what we have is a floor plans defines file, which is more extensive than what we had in our previous design, and I already set up a whole bunch of things over here. So let's just make that again tickle, and we have different things about the floor plan ratio, utilization, space to core, how we're going to make all the different stripes and so forth. And so that's already defined inside the floor plans defines over here. Okay, and back to my Innovus script so I can source that guy. And if I have a def already for my floor plan, I can read it in here. If I was doing scan, I could read a scan def as well. And now I'm going to create my floor plan. Okay, and I'm going to use just some sort of a definition that I made here. This is not necessarily the correct definition. So let's discuss a bit about full chip floor planning. At the block level, our design connected to the outside world through pins. We used the edit pins command to locate them around the block. There were many options. We had kind of a complex form or a really long type of a command where we could scatter our pins or place them manually one by one around the block. But at the full chip level, we don't have these types of pins that are the terminals of our top level. Rather, we have an I/O ring. So all of our ports are connected to instantiated IOs that we took from our IO library. We actually decided on, in our RTL basically, we made these IOs. We decided which type of cell we're going to put there and so forth. And then we have a particular site definition, which means that the IOs, they don't fit in standard cell rows. They fit in a different type of a row, which is an IO row, so it has a different site. And we place them around the perimeter of our chip. We can also put IOs sometimes in the middle of our chip, but I'm not going to go into that right now. Then we define the location of each IO with a special file, which is an IO file that Innovus provides us with its syntax and so forth. The IOs have power ground rings that are running through them, and one of the reasons that we put them in the periphery is that it's easy to make this type of a ring that connects everything. The rings are connected through abutment, so we saw in our last video that when we put a digital IO buffer next to a power supply cell, that it gets the VDD and IO. And these are specifically, they run around the chip in this ring, so we can see that we have 4 rings that are running around: VSS, VDD, VSS IO, and VDD IO. And then we put a cell on top of it, or a corner cell, or whatever we get, it is able to tap into those rings and get those voltages which it needs for its level shifters or for its ESD protection. So we need the IO fillers to continue these connections in the empty space. We're not necessarily going to put IOs right next to each other. This depends on our specific design and so forth. So if we have empty spaces, we're going to have to put a filler cell that is going to basically fill in these types of rings to connect to each other, and a bunch of other stuff. We have a special cell, which is a corner cell, that allows us to make this turn. So we don't have to make this abrupt turn. It's going to have these diagonal type of rings through it. So we put these corner cells on all the different corners. And what I see over here is I got my floor plan, which is a bit different than what we saw in the simple block video. We have these IOs now that are placed around, and actually the IOs are placed pretty much it spread them without any real thought about it. We can also see these little yellow things are the external pads. So if I go and I zoom in on one of these pads over here, so I'll zoom in on this guy, I can see that this is an IO, and it's called test enable, and I can actually select this thing and press Q, and it says in the attributes that this is test enable pad. So that is a pin for the design. But I see that, all of these yellow things, they're here around these 3 sides, and that these guys don't have any pins on them. So if I zoom in and look what these are, I see that this is a VSS IO. And in fact, all of the power was put here on the right side. That is not great. So I see that my corners here are all in one place. There are no corners in the corner. And if I go and I look at this, if I select these guys, I get the objects, which I can see that there are 4 corners and they're all in the same place. And what I want to pretty much do is I want to go and I want to deselect everything. I can do Control D, for example, to deselect everything. And I click on this icon, which is Move, Resize, Reshape without restrictions. And I'm going to click on it and press Q. It's going to show me that I got the northeast corner. That was maybe lucky that I got the northeast corner. I could have gotten a different one. So northeast would be over here. So I'll just click over here. And what I can see in my terminal, it said update floor plan object, and it said where it put it. So I can copy that line and put it in my script file, for example. Later on, I'll show you how to actually save the IO floor plan that I get. Okay, so now I'm going back over here. This is persistent, so once I click this move thing, it's going to always be on the move thing. I'm going to deselect everything again. I click on the move. Let's click over here, and I can see that it's going to be clicking on the southwest one. I don't really want that. I can try to get something else. How can I get something else? Well, let's try with the design browser, for example, to go into the IO ring and go down to a P corner, let's say the northwest corner. Let's click on that and see if it actually allowed me to grab it. And the answer is no. I still got the southwest corner, so I can like put it over here or something like that. That didn't work. Anyway, I can go and I can take this one, and what is this that I'm grabbed now? Now it's the northwest corner, so the northwest corner I can put over there. And I have left here, I have the southeast corner. And the southeast corner I can try to move as well. So I'll try to move it over there. And it did move. Okay, and what I want to do now is I want to move the southwest corner. So let's try to grab it somehow. So I'm going to click on that, and I'm going to do Q, and I've got the southwest corner. I got lucky that I got the southwest corner, and I put it over here. So now I have all of these corners, and they're in the right place, and I can already go, and I can file, save an IO file, and I can export my, my locations over here. So I can do OK. And now let's look at that file. So let's what did we have here? LP risk 5 top save IO, and I can see that my corner files, my corners, they are saved in this file, and I can use that later on. I will see that I will save such a file, and then I can load it in my design in a moment. So if I had an IO file that was ready, I could save it. So you see read IO file, and I can point to the IO file. If I don't, I can go and I can move things by hand, as we saw there, or prepare. We have all kinds of scripting and ways to prepare these files in a smarter way. I'm just going to use what I had there, but then I have the IO fillers. So I'm going to add the IO fillers, which should fill up my entire design. So I'm going to add the IO fillers. And I'm going to go back into my UI over here. I'm going to refresh, and now I see that everything was filled up with these IO fillers, and it's very important to see that everything was filled up nicely. If it was not filled up nicely, we're in trouble. So after adding our IO fillers, we also have to connect the special route of the pad ring. And remember, we had this route special command, which had all kinds of options in it. And let's just go remember, route, special route. We had all kinds of options, block rings, pad rings, floating, and so forth. And we just kind of clicked on it before in the previous video. But now we're going to go one by one on each of them throughout this video, because it is important to understand the difference and check the differences between them. So I'm going to go back, and I'm going to see that now that I have these pads, I have a pad ring underneath the pad. So I'm going to run this route special command. Sometimes this is needed, sometimes not. It depends on the way the lefts are built in our IO library. So I'm going to send that over, and it's going to do this routing, and it told me all kinds of things about it. And I can go back into my design over here, and I can see if it did anything, and it did add these like types of pins over here that are now connected. So there's pieces of metal on top of the ground and VDD, but it didn't really do anything. Sometimes I would have to actually add like a ring inside the IOs or something like that. Okay, so that was the next stage of this IO part. Okay, one thing that I can do is at each stage I can check DRC. So I will do check DRC and then minus type special. I don't want to check all the DRCs because that will be problematic. check DRCs. Well, let's check DRCs. Sorry, and I get 0 violations. So right now for that I'm good, and I should really check DRCs all the time while running Floorplan to see what my situation is. So it's time to place hard macros, and we have different types of hard macros such as SRAMs or analog IPs or all kinds of things that came as a hard macro. And we have two primary ways of placing the hard macros. The first way, which is the trivial way, is to manually place them. We have a move tool, and I'll show you that in the demo in a minute. And we can go and move our mouse around and put our macro wherever we want inside the floor plan. And then if we want to save that and put it in a script, we can look at the output log file and it'll give a update floor plan object command, which will show what the actual command is that we use to place it at a specific coordinate. We'll copy that into our script and we can run it next time if we want to rerun the floor plan commands. So that is one way, but we can actually do it a bit better by having some sort of structure, and that's using relative floor planning. So relative floor planning is using the create relative floor plan command with a lot of options, or using the GUI floor plan relative floor plan edit constraint, and that will open up this menu. And this menu is kind of complicated, so I'll just go over some of the features of it. But in general, you have a reference object, which is what we're trying to have our relative floor planning referred to. And this can be basically the core or die boundary or another object. So we can say go according to our core boundary, go such and such to the left or to the right according to one of the edges and so forth. So that is our reference object that we're going to be referring to, and it can be another object, so we can go and click on an SRAM that we already placed, get selected, it will fill in its name over here, and then we can use that as our reference and say I want it to be aligned to it or abutted to it or something like that. Then we're going to go vertically, horizontally relative to whatever our reference object was with a specific offset. So you're going to fill in these guys over here to say if I want it to be, relative to the top edge and this type of a distance and so forth. So it's something you'll have to play around with, but once you get it, you have this constraint that places things relative to each other. And then of course we can save the commands and rerun them in our script afterwards. So relative floor planning is a good way to do it when we have, say, a lot of SRAMs or something that we need to place and we want them to be aligned in some sort of way or something like that. So now I'm at the next place over here in my design, and what we're going to do is we're going to be placing the hard macros. Now I want to show you something before we start that. So let's go back to our picture over here, and I see that there are two things that we didn't discuss before. Now, note first of all that I am in this floor plan view, so this if I was over here I wouldn't see these. You see that thing disappeared over there. Okay, so in the floor plan view I see that there is this block called LP risk 5, which is a bunch of standard cells, and the utilization is 70% or something like that. That is the type of area that we expect it to take. But on the other side, what we can see here is we have these blocks over here, and these are the SRAMs. So if I look over here, this is ICC RAM 1, this is ICC RAM 0, this is DCC RAM 1, and this is DCC RAM 0. Okay, and what I have to do is I have to get them inside the floor plan. What I need to do is I need to place them right now. So the easiest way to do that, but the kind of dumbest way to do that, is to use this move resize again. So I would go click on that guy and stick it somewhere over here, and that is my SRAM. That's where I want it. Well, it's really hard to get it where I want it. You can play around with that, or you can jog things and so forth, but that's probably not the best way to do it. I have an undo button for certain things that works over here. So a good way to do it is actually using what we call relative floor plan. So if I go to floor plan and I go to relative floor plan, edit constraint, I have this form over here that you can see that has all kinds of options. First of all, you choose the object that you want to do it, and you can say take this object and give it place it relatively to something. What can you place it relatively to? Well, you can place it relatively to the die, to the core boundary, or to a different object. So if I want it to be a certain amount of microns away from a different object and aligned to it and so forth, and then I can exactly define that in this kind of UI over here. It takes a little bit of getting used to. Or you can then you can take the commands that it spit out in the terminal and copy them to your script. So that is something that I already did. So we start with a delete relative floor plan. That just deletes all of the relative floor plan constraints that we already made. I gave some comments over here about what the syntax is. I am going to get the DB object of imem0. Okay, so I got that, and now I have in imem0 name the DB object of or the name of of imem0, and I'm going to create relative floor plan. It's going to do it referred to the core boundary, and it's going to just show how it is. Let's copy that again. This is kind of a complex command to understand, so let's see exactly what happened when I did that. So what I can see here now is that if I look at my thing, I have placed this ICC RAM 0 at the bottom left, and it was placed at a certain distance from the left and from the left boundary, and it shows that this has this relative floor plan. If I go back and I do again the delete relative floor plan that I ran before, I just removed that thing, and that's okay. I could do that. It will just delete the constraint. It's not going to move it at this point. Okay, so I'm going to go back to my script, and I did the same thing for all of the floor plan objects. Okay, and what happened is now I have this relative floor plan for all of them. Again, I can delete the relative floor plan constraint if I want at this point, or I can leave it. I have deleted it for this guy, but I left it for the others for right now. If I go into the place view, I see that I don't see those arrows. So that's really for floor planning. And so I can now, you see that these are nicely aligned and they're put in the corner, and I left a little bit of room for routing on the channels and so forth. So this was kind of the way to make a relative floor plan, and you have to play around with these types of things. Next, we're going to go on to adding rings and halos to macros. So we have these macros over there, and we want to add a ring to them. There are two benefits for adding rings, basically. First of all, it's easy to connect the power and ground pins, the PG pins, to the ring. It's harder to connect the actual power and ground pins to the macro itself, to the power and ground pins on the macro, even though that can be really useful and save some space. But if we put a ring around it, then it's easy to connect our stripes to those rings, and to have any connection we want inside to the pins that are on the periphery, the VDD and ground pins that are on the periphery of the macro. So that is one thing if we put a ring around the macro. The other thing is it's easy to terminate the power mesh. So if we have a power mesh that's running along things and so forth, they terminate at the ring. They don't cause DRCs. It's a nice type of a feature to use. So you can choose to use rings around hard macros. It is not a must. You can save some space again without doing that. And you may want to only put a ring around a group of macros or something like that. So it comes at the expense of wasted area, and therefore SRAMs, we usually connect them from above by dropping vias. So they'll have on metal 4 or metal 5 pins, big pins of VDD and ground, and then with the the power layer that goes on top of that, it will drop vias on top of it. So that way we can kind of get power and ground into the middle of the macro without actually wasting room on the rings around them. Okay. To add rings to a macro, we're going to use the add ring command, or you do it from the GUI. Okay, and we can do something like add rings minus around selected minus type block rings, and the block rings are this type of a thing that goes around it. We can put a ring around all of them. We can put a ring only on several sides. So there are, of course, a lot of options in the add rings command, or we can use the GUI and do it kind of with a more visual type of a tool. Okay, so then after we put our rings around, we're going to add a halo. A halo is basically a placement blockage that we're going to put around our macros. We do not want to have the placer put standard cells very close to our macros, because it's going to be blocking pins and blocking access to the macro itself. So we're going to usually make this halo, and we have a command that does it automatically for us. So create place halo minus the instances that we want to place the halo around will automatically create this placement blockage around it, which will free up a lot of the area for routing and not have it blocked by all kinds of standard cells. Now that I've done that, I can go into adding rings. So one of the things that I can do is I can add rings around the hard macros. This costs with area, but it sometimes helps to connect all the VDD and ground pins of the rings. So I decided to do this, and what I'm going to do is I'm going to deselect everything, select the IMM0, and then put in add rings around that, put 3 micron width rings with 0.5 spacing, put them in metal 1 and metal 2, so let's see what happens when I do that. So if I do that, I'm going to go over here, and I can see that on my bottom guy over here, I have these rings that are in metal 1 and metal 2, and they have a nice big array of vias that connect between them and so forth. And so I have these nice rings around my SRAM over here. Okay, but there's another thing that I want to do, which is to create a halo, which means that I can't place any standard cells right there near the macro. So that's with create place halo. Okay, and I can see that now I have this pink area over here, which is a halo around the block, which is a placement blockage or partial placement blockage around the macro, so I won't do anything. So that's very much recommended to put a halo around it. You don't necessarily have to put rings. It's actually better to save space by not putting rings around there. So I'm going to do that to all of my memories. So I have that already here, and I can run that, and voila, I got rings around all of my macros and halos around them all, and life is good. I better check DRC before I do anything else. Okay, so I run the check DRC, and I see that there's still 0 violations, so this didn't cause any DRC errors already at this point. So next we're going to go over to special route, which we discussed in previous videos, but I'm going to revisit it now when we have a bit more complex a design. So special route, or SRoute, is a type of a router that only does specific types of routing. It actually does PG connections to pins and stripes. So it's going to do our power and ground connections, or special types of power ground connections. And we have this form here, which I'm going to use to demonstrate for you what the SRoute command, or the route special command, can do. So the first thing that we have is follow pins. So if we check this, it's going to route VDD and ground rails that are going to go on top of where our standard cell row is supposed to be. So in the GUI, we're just going to have these lines that are going to show where our rows are according to our teclef. Basically routing special route on the follow pins will drop metal 1, or depending on which type of process I'm on, it could be a metal 0 or some other type of a rail, that it's going to drop the follow pins which connect to our standard cells. So that's going to be done with route special minus connect core pin, or clicking on follow pins in the menu. It's really good to have the same name everywhere for all of the different options, but core pin, follow pin, or VDD ground rails, or something like that, they all mean the same thing. Block pins are the macro PG pins. So for example, the connections to the VDD and ground pins of the SRAM to connect them to the rings that we just set around our SRAMs. So that's going to be done with route special minus connect block pin, or selecting this selector here. As you can see, we can select several of these at the same time, and then SRoute will run on all of them. We can do minus connect core pin space block pin, and so forth, but that could take a longer time and be harder to debug. So I do recommend doing this one by one and making sure that everything worked out and there are no problems after doing each one of them. Next, we have pad pins. So we have the IOs that need to connect VDD and ground and so forth. They're going to connect them to the core ring or to something else, and that's going to be with route special minus connect pad pin, or over here pad pins. And we have something that's called secondary power pins, and that's if we have level shifters or special types of cells that have a VDD or ground connection that's not the main thing that connects to the follow pins, then it's called a secondary power pin, and we use the route special minus connect secondary power pins for connecting these types of connections. After doing this, we should check the connectivity of the special route. So if we do check connectivity, which is basically our LVS type of command in Innovus, we're going to get a lot of errors at this point because we don't have our whole design connected, we don't have signals connected, and so forth. So we're going to run check connectivity with minus type special, and then it will only check the connectivity of the special route. Okay, so if we do that, it should show us which VDD and ground, which PG pins are not connected inside our design. Now that I have my rings, what I need to do is I need to connect the block pins of the hard macros. So the block, which is the SRAMs over here, they have pins, they have PG pins, ground and VDD, and I want to connect them to whatever I can. So I'm going to run this route special. Again, that's the same special route that I had before, and I'm going to see that it connects the VDD and ground pins of the macros to the VDD and ground rings that are around it. And so I can see that this is going to take a little bit. It actually is routing quite a few connections. There are a lot of VDD and ground pins on the macros. And now if I go and I look into here, okay, I can see that I have a lot of connections over here. So these connections were VDD and ground pins of the macros, and they are now connected to the rings around here. So that made it easier. I could have done it in a different way, where I could bring stripes over that would drop vias onto the top of the macros. That is how I would save space. I'm not showing you that, not demonstrating that in this video. This way I really did that, and it helped. And let's see if it did it to all of the macros. Yes, see, that looks good, and that looks pretty good, and that looks pretty good. And I can also again do a quick check DRC and see that I didn't cause any new DRCs with that. And I see that I have 0 violations, so that is very good. So my next stage is I'm going to create a core ring. So this is going to be a ring around the entire core of the of my chip, basically, and that's going to be add rings minus type core rings, and I'm telling it what I want to do. So let's run that command. And so what I see happened here is I created core rings, which I defined over there to be in metal 2 and in metal 3, and I have a nice connection over here of a big array of vias and so forth, and I have these core rings, and they're very nice, and I can do, you know, a nice check DRC to see that I didn't cause any violations, and I see that I have 0 violations, so that's very good. So now that I have this core ring, what I can do actually is two cool things, or 3 cool things, I guess. First of all, I have my my pads over here. So my pads have VDD and ground pins. You see that there are ground pins on this pad over here because it's a ground pad. And now I can take this net and I can connect it very easily to the ground ring I have over here. So it's much easier now to connect it. Now, you should know that it really depends on where I put these IOs. It could cause all kinds of DRC violations, because, for example, if I want to route this, I'm going to have to go and keep distance from this VDD array of vias and so forth until I get to the ground pin. But these are things that we really have to play a lot with. Again, I didn't take any thought into where I put the IOs over here. It was really just whatever the spread that the tool gave me. That is not what you are supposed to do. But anyway, so now that I have that, so those are the pad pins are going to connect to these VDD and ground rails, the pad VDD and VSS. The second thing is we have the follow pins, which are the standard cell rows. So I'm going to have rows in metal 1 all over here, and the rows can easily connect on these 2 sides to the rings, the VDD and ground rings. And when the rows are over here, they can easily connect to the rings that are around the macros over here. So that makes so these rings, they make easy connections and so forth. Okay, and the third thing we're going to do is we're going to build our power grid, which is the stripes. So we can then send like a stripe in metal 2 or in any metal we want up above, and they can go from ring to ring and connect down to the rings, and they can go from, you know, the ring to ring of the SRAMs without causing any trouble. Okay, so that is what we're going to exemplify now. So the first one we're going to start with is the follow pins. The follow pins, or special route type core pin, is going to connect the standard cell rows. So I'm going to run that command. And what do we see happen? We have all this blue. Blue is metal 1. I can zoom in over here, and I see that I got these core pins, and you see that this core pin is ground. Okay, and it is connected over here with nice vias to the metal 2 on this layer over here. And I see that it's really nice to terminate these with these rings that I have over here. They terminate very beautifully and probably don't cause any DRCs. So that's why I also like to use these rings, even though they do waste quite a bit of area. The second thing is I can look at the sides over here, and I see that the VDD and ground, they terminate in these metal 2 stripes of the core rings. Okay, so I have that very nicely as well. And of course, now I should run another check DRC to make sure that I don't have any problems over here. And I see that I still have 0 violations, so that is great. Okay, so now I connected my follow pins. So next thing is, again, I have on the pads, I have the VDD and ground, and I want to connect to the core rings. So I will run this, and it should connect the pads, the VDD and ground of the pads, to the core rings. So let's run that. I'm going to, again, open up my UI, and remember that all of my VDD and ground pin pads were on the right side, and I can actually see these little things over here. Those are really my connections. So I had this VSS IO59. It had these ground pins, and you see that it made a connection over here, a very strong, robust connection to ground over here. And so these are the types of things that we're going to try to do. We can go down and see what these are also VSSs, right? All of these are VSSs that are connected, and that is what I kind of wanted to do. Okay. The VDDs don't have any pins on them, this type of VDD, so it didn't need to connect anything to the rings over there. So this one does have pins on it, so you see that it connected the VDDs to this ring over here, and this one as well connected the VDDs to the ring. Of course, this is very bad distribution of my power. Again, I told you I just took something that was very default by the tool. This is not how you should do it. But you should check the RC after you do this, of course, and make sure that everything came out okay. I may be lucky over here and I have 0 violations, but you're probably going to run into violations, and you're going to want to probably move around your pads, maybe move around your macros and so forth until you get a clean DRC over here. You can also do all kinds of wire editing thing to really clean that up and put it inside your script. So here's a small reminder about Endcaps and well taps, which we're going to be putting down next. So Endcaps, also known as boundary cells, are cells that are required at the end of standard cell rows. So you see here, these are the Endcaps. So in advanced processes, they're more complicated than that. We're going to have them at the top and the bottom and at corners. We really need them in order to terminate the rows and terminate the areas we're going to have standard cells for all kinds of DRCs. These Endcaps, they include polys, ODs, NWELs, all kinds of layers that are needed to terminate the standard cell rows and to ensure that we are clean with DRC after running placement, and we have enough density around those areas. So those are called Endcaps, and we have different types of DB commands, such as what the cells that we're going to use for add Endcaps left edge, add Endcaps right edge, and we have a whole array of these. And then we're going to run the add Endcaps command, and we can add a prefix, so these instances will be called Endcap 1, Endcap 2, and so forth. Next, we have well taps, which are similar in a way to Endcaps. Sometimes we actually will use well taps to implement Endcaps, but the well taps have a different job, and their job is to connect VDD and ground to the NWEL and PWEL, which will enable us to prevent latch up. Okay, and these we have a DRC that requires us to spread these out every once in a while, and you can see that we have these well taps which are here, and they have some sort of minimum distance between them. If you remember correctly, say this is a VDD rail over here, this follow pin over here, then what it means is we're going to have an NWEL on top and on bottom of them, and if we put one well tap over here, then it's going to have a connection to VDD, and that's going to be sufficient for all the NWEL that's over here. And that's why the distance, if we do a staggered type of design, is enough. We only need one in every other row versus in every row. Anyway, you can choose these things in the add well taps command or the GUI, and you can say if you want it to be staggered or you want it to be in every single row and so forth. And there's also a check well taps command, which will enable us to check that we have sufficient well taps throughout our design before we actually go run a full DRC and see that we have a DRC for too far a distance between well taps. So my next step is going to be Endcaps. So some libraries, most libraries have Endcaps. There are different levels at advanced processes. You're going to have a lot of these Endcaps. They're kind of a dummy type of a standard cell that helps us end standard cell rows very nicely. So I'm going to use this add Endcaps. I set up in my settings all kinds of options for that. Okay, and now I can go back to see what happened over there, and let's just go into I'll take off all the routing layers so I can see these, and I should have cells that were added to the end of rows. So you see end cap ties over here. These were added to the end of the rows. If I put on my metal 1, you see that these are connected here at the end of the standard cell rows before they go to the end. Okay, I can see them here as well in the full view. Okay, so I have these end caps all over the place. Again, let's turn off and see what I can see here. Zoomed out, we don't see them much, but I get these end caps all over. I should have them also near my SRAMs as well. So I had to end the rows, so it put the end caps over here and over here, and that looks like it's okay. Next, I'm going to be adding my well taps, and I have some sort of a cell that's going to be my well tap cell. I have all kinds of options. I chose the checkerboard option to put them in, and I have to decide on the cell interval, and I also have to, afterwards, I have to check that I put enough of them with a check well taps command, and the well tap rule is set by my DRC rule deck, so I have to go and check that out and make sure I have it. So let's add the well taps. And now I see, I mean, this is more kind of clear. I see there are many more well taps, and I see that they are this checkerboard type of an option. So if I put on my metal 1, I see that one is between these two rails and the other is between these two rails, and these are the well taps that are around my design. And when I ran the check well taps, I see that I got 0 violations, which is very good. So this is another important thing, and you may have to also consider things like power domains and such when you run it. So I added my well taps. Sometimes different halos and so forth can bother me, so I might need to do some manual intervention to get really good well taps. You have to obviously check this with the sign-off DRC deck to actually make sure that you did this correctly throughout your design. Next, we're going to go over to power planning. And one of the most important, the most important part of floor planning undoubtedly is creating the power grid. It is a real problem. It is going to ruin a lot of our chips, hopefully not. But we're going to have to really spend a lot of effort in making our power grid, checking it, and so forth and so on. I don't think I talk about it as much as I should in my course, and probably here either. So I'm just going to put that as a bullet over here. But this is a real important subject, and there's actually not that much documentation on it in the different tools and so forth. They give you kind of how to do it and how to do it well. I think that's because it's different for each chip and each process, and there's a lot of knowledge and experience that needs to go into this, and a lot of checking as well. Anyway, the goal of power grids is to provide VDD and ground to all circuits. And we're going to use a power grid usually to do this, which means we have vertical and horizontal rails at different levels that are going to have interleaved VDD and ground, and these via stacks that go between them. And we're going to cover our whole chip basically with that. Sometimes we'll have a ring around the core of the chip to enable good connections to that. Okay, so why do we have this power grid? Well, it's going to help us minimize IR drop, which is basically the resistance that is between a certain standard cell or a certain transistor and the actual input of the VDD or the ground is going to cause IR drop because there's going to be current running through that. It's going to go over the resistance, and we're going to have a voltage drop. And instead of getting VDD at that cell or that transistor, we're going to get VDD minus delta, or instead of getting ground, we're going to get delta V. And that is going to hurt whatever characterization we make and cause errors. So that's static IR drop. And the other one is dynamic, or DI to DT drop, which it means that we are able to provide sufficient current when we have a change in the amount of current we need. So these are very similar to each other, and it just means that basically our cells are going to work as we characterize them, as we check them in timing and so forth. We need to provide a very robust power grid and a lot of capacitance that's going to provide us with the current, the immediate current locally that we need to feed our transistors. Then the next thing, of course, is electromigration. So we're going to have a lot of current running through the wires, and if we have too high a current density, then after a while we're going to have an open or a short on wires, and so we must meet our electromigration requirements so we get reliability in our chip. And finally, we need to leave enough room for signal routing. If we just cover the whole chip with power grid, then we're not going to be able to route our signals, and then we're not going to be able to make our design. So that's kind of a trade-off here of how dense we make our power grid versus how much area we actually have for routing. And how do we check this? Well, there are different types of power rail analysis tools out there. Cadence provides Voltus. There's also Red Hawk. There are other ones. And that's beyond the scope of this demo, but it's really important to check both early rail analysis that we think it's going to work, and after we finish actually our whole design, to do sign-off IR drop analysis, electromigration analysis, and total power grid analysis. So that's beyond the scope of this demo. Maybe in the future I will make videos about how to do these types of things as well. Okay, and now I'm ready to create my power grid, and this I'm going to do at a very, very simplistic level. I'm not really creating a power grid. Creating the entire power grid is quite complex, and it's a methodology that you have to do over here. But I'm just going to put stripes on metal 2. I'm not going to build any higher levels. That is not what you would really want to do. You really have to consider how you want to make your power grid and check with early rail analysis, and later on with real EMIR checks that you have a robust enough power grid. That I'm not showing in this series of videos, but I'm just going to show you how you would create such stripes. So what I'm going to do is use the add stripes a command with several options, and let's see what it does. Okay, so I did that and I don't see anything. That's because metal 2 is turned off. But once I turned on metal 2, I see that I added the stripes. Let's add all of the layers actually. And I see that the stripes were nicely terminated at my rings. I can see that everywhere that a stripe went over a follow pin, a VDD and ground rail on metal 1, I dropped vias. And so that looks very nice. And I have to see that they terminated nicely at the SRAMs. So they didn't terminate very nicely. You see these jogs, these are very ugly. That is not something that you really want. Maybe if I would have moved my my SRAMs a little bit to the right or to the left, I could get rid of that. Maybe if I was just dropping pins from the top level, then I wouldn't have to see that. So these are not very nice things, but I got to check DRCs and see if that worked well. And so I run my check DRC, and often you will have lots of problems over here, but I still am lucky and I have 0 violations. So I have my power stripes as well. And so basically now I finished writing my floor plan. I have this end stage command over here, which is going to do all kinds of checks at the end and create all kinds of reports. And once I finish that, I'm also going to write a def out. So do you remember that when we did the physical synthesis, there was an option of taking a def file? And so I will do this write def to save it, and I can use that afterwards. But before that, I see that I added a message here that I can use delete DRC markers to remove any DRCs after looking at them. So let's look at them in a second, and the runtime that it took me to create this while recording it was actually a long time, 51 minutes for this small design. But let's see if I have any violations over here. So I'm going to go over to this violation browser, and I see that there are quite a few violations. So you see that there are antenna or dangling wires over here. So let's go, and we see that this is something that is that it does not like. So that is a type of a dangling wire that we don't like over there, and there are several of them in the design. So you see that is something we should get rid of. Okay, it's a place for a DRC. And there are these opens. These are connectivity checks. I got them with the check connectivity minus type special command, and I see that they're on VDDIO, and let's see that. And I see that all of these checks, all these problems, they're on the IO pads where I connect them, and this is something that you should not pay attention to. It has to do with how the left was written and so forth. So I don't have, I will continue to have these types of violations until the end of my design, until the end of my run over here. But so I just know that I'm going to have these 8 opens in my check connectivity. Now, once I finish that, I can do the delete DRC markers, and those things will go away. And when I open up my violation browser, I don't have any more violations. So that's something every time I run some sort of DRC, I should do to get rid of my violations. But I told you that I had my markers over there. So let's just show where they came from. So I run check connectivity minus type special minus, and I also have something else that is called ignore unrouted nets that I want to run at this point. So it's going to run that, and it found these dangling wires that I can see with the X over there. So we have a little script that we wrote to get rid of these dangling wires, and it is called trim dangling wires. So it's inside the procedures, and when I run that, look at that, it automatically fixed it. We see that is no more. And if I now do my check connectivity again, I'm going to see, voila, that disappeared. And I'll look at my design browser, and now all I have is these 8 opens. So my life is really good right now. Okay, and I can again do the delete DRC markers and get rid of any of the markers that are left over. So that kind of finishes my floor plan. Again, what I want to do here is write out my def. Once I wrote out my def, I can load it later just to have my floor plan that I finished and start from that place with placement again, or I can go and use it in my synthesis to provide a good basis for physical synthesis.